Okay, hello everybody. I thought what we'll look at today is hypothesis testing, which is something that I know some people struggle with initially to get their ideas around. Basically, it's the conclusion at the end that I think people struggle with mainly. So I thought we'd look at June 23 stats paper, so last year's paper, and there was 2 hypothesis questions on there. This one, question 2, which is just a basic hypothesis testing, but there's a bit of a lead up to it. And then there's one a little bit later, question 5, which is to do with hypothesis testing for sample means, and we will look at that in a later video. But this one here, so going through bit by bit, a little bit of a lead up before we get to the actual hypothesis testing. So this is all about machine filling packets with sweets. And 1/7 of the packets, it says, contains a prize. And they say the packets of sweets are placed in boxes before being delivered to the shops, and there are 40 packets of sweets in a box. And we want the random variable t representing the number of packets of sweets that contain a prize in the box. So if t is the number of packets that have a prize in it, and it tells you they're binomially distributed, we've got 40 packets in our box, and each one has a probability of 1/7 of containing a prize. So the first one is just a straightforward 1 marker about, do you know what conditions you need to have to be able to use the binomial distribution? So it says state a condition needed for t to be modelled as binomially distributed with 40 as our number of trials and 1/7 as our probability. So the things to really concentrate on there, the probably 2 main things, is firstly our probability, 1/7. We are assuming that every single packet has the same probability of 1/7 of having a prize in it. So we need to say that that probability is a constant. It stays the same. So we're looking at, for part A, talking about constant probability. The probability never changes from 1/7 as you go from packet to packet. Okay, so constant probability will be one of the things that we could look at. The second thing that we'll probably focus on is independence. And what we mean by that is every single packet, whether they've got a prize in it or not, has no effect on the next packet you look at. So each packet is independent of the next packet. Doesn't matter if you've had 10 in a row where they've got a prize in them, and you're kind of going to go, well, it's not likely surely the 11th will also have a prize, but for binomial you have to assume that the 11th one, it doesn't matter what's happened in the ones before them, each one is independent of each other. So we're looking at each packet is independent of all other packets. And those are probably the 2 main things to focus in when they have that question about binomial, what makes a binomial distribution. And we're looking at, right, probability's got to stay the same all the time, and every single trial, and we've got 40 trials here because we've got 40 packets we're looking at, every single trial is independent of the other ones. Okay? Right, it then moves on to quite a nice, straightforward, the part B. It's just, can you use your calculator? And nowadays with our nice graphic calculators, we're just going to look up the binomial distribution and we're going to pick out the probability that we need. So we just need to put in that n is 40 and our p is 1/7 into our calculator. The first thing they want to say is find the probability the box has exactly 6 packets. Exactly. So we are just looking up probability t equals 6. And that should be a nice straightforward into your calculator. Using those parameters, put in t equals 6, and apparently, I've looked at this before, you get 0.17273, so I'll just call it 27. Now I always give it to 4DP. They will accept anything which rounds to 0.173 here, anything to 3 significant figures, and that's kind of your go-to really. But in olden times when we used to use tables, it was given to 4DP, so that's always a nice standard thing to go to. The part 2 for B is, and you've got to get the wording right here, the probability that a box has fewer than 3 packets containing a prize. So fewer doesn't include 3. It's not at least 3 or something like that where it would include 3 and go above, but fewer than 3, we're not including 3. So we are looking up the probability that T is less than 3. And you can do that with your cumulative, and obviously you won't put 3 in because you wouldn't want that. You won't want to include 3. So you're going to probably put in to your calculator, T is less than or equal to 2. So you're wanting 2 and below. Okay, and again, we should know how to use our calculators now, but we're getting to the stage where if we don't, that's something we need to address. Put that into your calculator, out pops the answer. So in this case, it's 0.0313, I think it is, if that's correct. Yes. No, it's not. There's a good one. I can't even read off my calculator. So it's 0.0616. There we go. That's better. Okay. So we have our 2 basic probabilities they've asked us for there. Okay, now it's going to start getting a little bit harder. So that was 1 mark for your stating your conditions for your binomial, and then into simple little bit of 2 marks where you're just using your calculator to find some probability. So it's a nice start. 3 marks, 3 easy marks should be. Now this next one, we have Camille's sweet shop buys 5 boxes of the sweets. And you've got to find the probability that exactly 2 of these 5 boxes have fewer than 3 packets containing a prize. So this is one they like to do where you start off with a little binomial, you work out a probability, and then they're going to do a binomial of a binomial. So, because what they're going to focus in on is they want each box to have fewer than 3 packets. Well, that's what we've just worked out. That's the probability a box has fewer than 3 packets. So we're going to look at a new variable now. We're going to look at the number of boxes that Camille's Sweet Shop gets, which is 5 boxes. So it's a new binomial. We can call it whatever we want. So we could call this y, let's say. Let y be number of boxes with fewer than 3. Okay? Okay, fewer than 3 packets contain a prize. So, we've now got y, this number of boxes. We know that they're getting 5 boxes, so that's our number of trials. And we know the probability that 1 box has fewer than 3 packets containing a prize is this probability. So we're using that probability in a new binomial. And this is something they like to do. So it's going to be 0.0616 in there as our probability. Okay, so they love this idea of, oh, you do a bit of binomial, work out a probability, and then you use that in a different scenario. Okay, so now we're putting those numbers, n is 5, p is 0.0616 into our calculator. Maybe use the fuller value here, don't use the rounded value, although they give you a little bit of leeway there. They're allowing you, if you use they give you a bit of a range of answers if you use a rounded off one, but don't make it too rounded. You know, don't put 0.06 in. You know, let's give it a bit of more accuracy than that. And we want, what do we want again? Exactly 2 of those boxes. So we want the probability that y equals 2. Calculator job again. In we go. N is 5, p is that. We want exactly 2, so we're looking for a spot-on particular calculation. On my calculator, my computer's just gone, so I can't see the question again. Give me 1 sec. Put it into your calculator, and it comes out at this is the 0.031, 0.03134, whatever degree of accuracy you want to go. I think they accepted anything in the range 0.0313 to 0.00314. There we go. Okay. So, all done. Nice simple bit of binomial. They're binomial of a binomial, they like that one, so look out for that one, using that probability into there. Okay, now comes our hypothesis test. So, just clean the board a bit. So, just get that calculation back up there. So it now says a random sample of 110 packets is taken and 9 packets contain a prize. Camille is claiming that the proportion of packets containing a prize is less than 1/7. Okay, less than 1/7. Gone down, okay, and it's going to be important that it's less than 1/7, that it hasn't said it's not 1/7. Less than 1/7, so it's specifically talking about a direction for this probability that's gone down. Using a simple test, assess Camille's claim. You should state your hypothesis clearly. Always get a mark for stating your hypothesis. So even if you're struggling a little bit, just get that hypothesis down and there's a mark straight away. And we've got a 5% level of significance on this. So what we're going to do, first of all, we've got to state our hypothesis. So we're assuming that, and you always assume nothing's changed. Everything stayed the same. So your null hypothesis is always whatever was the case beforehand is still that case. And then your alternate hypothesis is now it's changed. So our null hypothesis is going to be that this probability of getting a prize is still 1/7. So our H0 is going to be that P is still 1/7. Okay? However, Camille is suggesting that prize is now less than 1/7. So your alternate hypothesis is that P is now less than 1/7. Simple mark, just for quoting those. Okay? It's a one-tailed test. If this was that the probability has changed, we would just have not equal to 1/7. And that's when you have to split your 5%, 2.5% one side, 2.5% the other side. 2.5% it going down, 2.5% it going up in terms of the probability. Right, we've got a simple situation where we've got some numbers. We know there are 110 packets, 9 of them contained a prize. Now, if there was 1/7 actually contained a prize, you would expect 1/7 of 110 to be how many actually have got a prize in it. And that's a lot more than 9. Well, not a great deal more than 9, you know, but you can work that out quite easily, you know, around the 15, 16 mark. We're getting only 9, so that's kind of less than we would expect. So actually, Camille, you can see how maybe Camille's got a point here. Perhaps it's not 1/7 and actually it's gone down. But our job is to work out how likely are we to get a result of just 9 out of our 110. So we're going to look at 9 out of 110. We're going to go, right, so let our T now be binomially distributed, 110 packets we got, and we got our P where we're thinking it's 1/7. Now the thing is, you don't just look at 9. We know we've got 9 out of 10, 110, sorry. But you don't just look at 9, because each separate probability, each separate number, is actually going to be a very small number. Even if you look at like the most likely value, you know, 1/7 of 110 would be the number of packets you would expect to get having a prize in it. That's like 15, 16. That's still going to be a small number, because our probability, we know all adds up to 1, is distributed amongst 110 numbers, all the way, well, 111, all the way from 0 up to 110. Now 15, 16, those should be our most popular numbers, but they're still going to be really small probability. So we don't just look at the result we got, we look at the result we got and potentially a worse result than that. Now if you're expecting 15 or 16 bags to contain a prize and you've only got 9 turning up, what would be worse if you only had 8 turning up, or 7, or 6, or 5? So you look at the probability of 9 and below. So we're going to look at the probability that T is going to be less than or equal to 9. The result we got, or worse than that result. Now, we look at that total probability and we see how likely is it to get that case. So we go to our calculator. We put in 110, we put in our 1/7, because that's what we're assuming, it's still 1/7. And we look at 9 and below, so it's a cumulative one. So we're going to have to go to the cumulative binomial. We look up that probability, and out comes, let me have a little look, 0.03829. There we go. Okay. Now, that is the probability of getting 9 packets or below if 1/7 is correct. And the whole point of probability hypothesis testing is basically saying, how likely am I to get this result, and am I happy with the probability I've got there? Now, the happiness is when you compare it to the level you've been set. So if this is, the sweet manufacturer setting this up, they are going to say, right, okay, well, at what point do we start going, this looks a bit suspicious. It looks like our 1/7 is going to be not correct. And they've set the level at 5%. If we get a level result that's lower than 5%, that's so unlikely that it's below 5%, that's when we go, there's something up here, and this p can't be equal to 1/7. And as we can see, our result, 0.0389, that's 3.8%. It's lower than 5%. So that's really, really unlikely to happen. So now that's when we compare it with the significance level. We go, we've got a result of 3.8%, which is less than our 5%. And because that is so small, it's so unlikely to happen, it's big suspicions on this. This doesn't look like it's right. So we assume this is right, and when we've assumed it's right, if we end up getting such a low probability, it's telling us that's really, really unlikely to happen, that's when we're going, right, that's not good enough, we're going to reject that. So now we reject our H0, and, as always, put it in context. So this is therefore saying that we're going to assume that Camille is right. So Camille's claim, there is evidence, let's go down one here now, is sufficient evidence to support Camille's claim that the proportion of packets containing prize is under 1/7, or the probability of getting a packet containing prize. As long as you show that you realise that what that means, rejecting H0 means in the context of this particular question. So there you go, a pretty nice little hypothesis test question from last year. It was worth 9 marks in the end. The last 4 marks for the hypothesis testing bit, but it's quite a classic one. So don't forget, check, is it 1-tailed, is it 2-tailed? Am I looking at 5%? Or if this was not equal to 1/7, we'd be looking at 2.5% that we would be judging our probability against. Okay. Hopefully that helps. I will do the other hypothesis test and sample test. I think it was question 5 on a later video for you to look at.